Okay, the exercises from problem set 9.1e are some of my favorite problems because I think of them as being real world or having some, day-to-day applications for you, and you can see where chemistry really is used in virtually every area of your life. So, number 11 says, a bag of road salt used to melt ice and snow from roads contains a mixture of calcium chloride and sodium chloride. A 2.765 gram sample of the mixture was analyzed by first converting all the calcium into calcium oxalate. So it was CaCl2, and they converted it to CaC2O4. But you can see it's just still one calcium ion in either compound. This 2.765 eventually will need, but remember that's both compounds, the sodium and the calcium salts. So then the calcium oxalate was dissolved in H2SO4 and titrated with 0.1 molar KMnO4 solution. Now, the H2SO4 is only important because you need an acidic solution for this redox to take place. But as far as factoring into the calculations, the H2SO4 will not. It's just another way of saying in an acidic solution. So what you need to look at is the fact that you've got CaC2O4 being titrated with KMnO4. And then they say you produce Mn2 plus CO2 and H2O. Now you notice that the MnO4 is accounted for, the C2O4 is accounted for, but there's no mention of either the calcium ion or the potassium ion. And that's because these are all going to be aqueous. So this is aqueous, this is aqueous. These ions, by definition, are aqueous. CO2 is a gas that's going to escape. H2O is a liquid. So we can assume the Ca and the K are also aqueous, so they'd show up on the other side. But the easier thing to do is just eliminate them here and put our -1 and our +2 charges. Calcium and potassium are merely going to be spectator ions in this reaction. So I'm just going to go ahead and get them out of here. It'll be one less thing for us to keep track of. So looking at this, if I go ahead and attempt to balance this, well, I guess I'll start with A because B has me do the half equations. But A says, what would be observed at the equivalence point of the titration? And what they're expecting you to know is that permanganate is purple, and when it is reduced, it becomes colorless. So the change I would see is my solution would go from purple to colorless. And don't use the word clear when you mean colorless, because there is a difference. B says, write the half equation for the oxidation starting with C2O4 minus 2. Oh, I'm sorry, yeah, that should be a minus 2 because the calcium is the +2. So let me just correct that. So my half equation for part B, C2O4 is becoming CO2. This has got a -2 charge on it. I need 2 carbon on this side to balance that. That also gives me 4 oxygen, so I'm good. This is the more positive side, so I add 2 electrons. And that's all there is to that first half equation. C says write the half equation for the reduction of MnO4. So MnO4 is a -1, and it's going to become Mn2 plus. My manganese is balanced, but I need 4 H2O on the right, which means I need 8 H plus on the left. And now as far as balancing my charge, I've got a +7 and a +2, so I need 5 electrons on the left side or the reactant side. So write the overall equation for the redox. I'm going to have to take my first half equation and multiply by 5. I'm going to have to take my second half equation and multiply by 2. And when I combine those then, I'm going to go ahead and take a fresh sheet here. My combined equation for D is going to leave me with 5C2O4 with a -2 charge, 16H plus, 2MnO4 minus, and then on the other side 10CO2, 2Mn2 plus ions, and 8H2O. Then, using that equation, I'm asked to calculate how many moles of C2O4 was in this, were titrated here, or were in my solution. So what I know is that I had 0.02465 liters of the KMnO4 used. I could put a 0 there so it's not confusing. Use 24.65 milliliters, or 0.02465 liters, and it has a strength of 0.1 moles per liter. So when I multiply here, I know that I started with 0.002465 moles of the MnO4 minus. And when I look at my balanced equation here, I see that I can expect 6 C2O4 ions from every 2 permanganate ions. So using my ratio of 5/2, I can assume I had 0.00616 moles of the oxalate ions, or C2O4. So then, how many calcium ions would that be? Well, calcium is a +2, so calcium is 1-to-1 with the oxalate. So I would also have 0.00616 moles of calcium ions, or calcium oxalate. So then in part G, when I'm asked to calculate what's the percentage by mass of calcium oxalate in my original mixture, I could take my 0.00616 moles of calcium oxalate, and I figured out that calcium oxalate weighs 110.9 grams per mole, giving me 0.676 grams of the calcium oxalate. And if I slide this up just slightly, based on what I was told, 0.676 out of the total of 2.765 times 100% means that the calcium oxalate was 24.7%, and the other approximately 75% must have been NaCl. Number 12 talks about how they use a breathalyzer to determine your alcohol level. And I believe in the state of Minnesota, 0.08 is what's considered legally intoxicated. And that is expressed as a mass percent. And so this problem is going to show you exactly how the calculations occur. So it says alcohol levels in blood can be determined by a redox equation, and this one's actually a blood draw, but the breathalyzer works in very much the same way, which we'll get into more when we do our medication unit. But it gives you the equation here of potassium dichromate, or the dichromate ion, which is right here. That's what they're using for the test. And then this represents the ethanol, or the alcohol that you're testing for. I can't get my L there. Okay. So you had ethanol reacting with the dichromate, and here's the balanced equation for it. And it says determine the alcohol percentage in the blood by mass if a 10-gram sample of blood requires 9.25 cc's of 0.055 molar potassium dichromate to reach equivalence. So this is actually quite easy because they've given you the balanced equation. So I'm going to take my cc's and change it to 0.00925 liters. I'm going to multiply by the 0.0550 moles per liter, and I find out that I have 5.0875 times 10 to the minus fourth chromate ions, or dichromate ions, I should say. And once I know how many dichromate ions I have, I can see that I have 1 mole of alcohol, C2, H3, H5, I mean, OH, my ethanol, for every 2 moles of the dichromate, Cr2O7, 2 minus. So that means I have half as much, or 2.54 times 10 to the minus fourth moles of the ethanol. And now that I know how many moles of ethanol I have, I can go ahead and multiply by the mass, the molar mass of ethanol, which is 46.08 grams per mole. And I see that I've got 0.0117 grams of alcohol in the bloodstream. Now that doesn't seem like much, but if I actually do this as a percentage, 0.0117 divided by 10 times 100% gives me a 0.12%, which exceeds that 0.08. So doesn't take much alcohol in the system to lead to you being impaired. And B, what would be the test result? What would I notice the color change during the titration? It would change from orange to green. And I always remember this one because when you change from orange to green, green means go to jail.